Hello everybody. For this last section, we're going to talk about measuring earthquakes and how we do this. The first scale we're going to look at is the Modified Mercalli Intensity Scale. You might see this as the MMI in some places. This is looking at the most intense shaking at a particular location, and because the amount of shaking depends on how far you are from the earthquake, the measurement of the earthquake on this scale is going to vary depending on how far away you are. This is something that is based on descriptive information, what people saw and felt and heard and observed whenever the earthquake took place, depending on how far away they were. And we measure this from 1 to 12, which is also much more useful to people who are not scientists. You can imagine a situation where we have an earthquake which took place 500 years ago. There were no seismographs in the world at that time, as far as I am aware, that would have been able to give us good numbers on the earthquake. Instead, what we would have are historical records. We go around and we have this person's description of the shaking they felt, and this other person talks about how they saw the buildings doing this, and we put all of that together and use this scale for it. And you can see there's a lot of different degrees that we can use for this. Again, this is descriptive. There's no hard numbers here, so there's not always an exact right category for the earthquake to go in. But it might go into one of these buckets, right? The weak bucket, earthquakes which happen every day that you might not even feel or notice at all, to earthquakes which you would definitely notice, but maybe aren't much stronger than it takes to knock you off your feet if you're a little off balance, all the way to earthquakes which could take down buildings, cause the loss of life, or even, in some cases, completely level an area. We could also talk about, for the scientists, the Richter magnitude scale. And we talk about magnitude, we're looking at the amount of energy in total released by the earthquake. This is something which is directly related to the size of the fault surface. You would imagine for a very, very small fault surface, whenever we have slip along it, there's just a little bit of energy, as opposed to a case where we have a huge fault surface. Whenever there is motion along it, there's a tremendous amount of energy being released. This is something which we record quantitatively. We record this with data, hard numbers, using the seismograph. And this is something which is on a logarithmic scale. So going from a 7 magnitude to an 8 magnitude is 10 times more movement, or about 32 times more energy. Going from a 7 to an 8 to a 9, though, is 100 times more movement, or about 1,000 times more energy. And this gives you an overview of some of the strongest earthquakes we have ever observed. Things like earthquake in Chile, Alaska, one from 2011 in Japan, which we'll actually be looking at more. Earthquakes here on the left, everything from magnitude 2 all the way up to 10 here. And some of the energy equivalents on the right, things we might be more familiar with. Nuclear weapons, to tornadoes, to lightning bolts, Krakatoa volcano, as well as the energy release over here. You'll notice, of course, that the number of earthquakes that we get that are very small is a huge number, and that as we go up, we get to a very small number of massive earthquakes. So, if I remember this from one of the earlier units, we have our slow S waves coming in later, our fast primary P waves coming in first, and there's this time difference between them, maybe 25 seconds here. So we can note this down, it's maybe close to 25 seconds there. We could also look at the amplitude of the biggest wave that we have, the maximum intensity wave. We can see that it's maybe 25 here, 25 millimeters that is, on the seismograph. And we could draw a line from here to here and cover everything in between where we have our magnitude scale and see that it is right at about a 5. This map here has the largest earthquakes we've ever recorded, 1 through about 17 on this map. I'm going to take a second. Where are these? These are going to be on the outside of the Pacific Ocean, Pacific Plate, wherever we have these conversion boundaries, wherever we have this plate subducting beneath continents. So the maximum magnitude of an earthquake, what is the biggest earthquake that could happen? So the scale itself doesn't have anything like this. You could have something that is higher than, say, a 10, but the limit on this one is the size of the Earth. If you had something which is a magnitude 12 earthquake, you would need a fault surface which is bigger than the Earth itself, making this, it would be very creative to do, let's say. The USGS has all the information about earthquakes. It is the government agency responsible for this, the U.S. Geological Survey. And this, of course, has uses for domestic hazards, saving people's lives. There's also, of course, the fact that if there were some sort of nuclear weapon detonated on the other side of the world, these, the ears which are always listening, would be able to pick that up very, very quickly. It would be sort of difficult to hide something that big. There are a couple of hot jams here. Those of you who would like to learn this information from somebody who isn't me, take no offense. What are the big ideas for this section? It pertains to earthquakes. First, what are the earthquake basics? What is an earthquake? What happens? How would you describe what happens in the earth physically? And what are the most active locations in the US and in Arizona? What are the types of faults? What are primary hazards and secondary hazards? What is the difference? What would be an example of each? What are the different types of waves from an earthquake? And how can we use these waves to image the interior of the Earth? Thanks.